Hi, this is the last exam I have to go through for the midterm 1 content that I'm doing for MA 266. This is the final from spring 2017, and we're only going to be going over all the content for exam 1. Question 1, let y of t be the solution to this initial value problem, and we're trying to find y of 2. So first off, we're going to need to isolate y prime. That's going to give us y prime plus 1 over y is equal to 3t minus 2 plus 2 over t. And when I say 1 over y, what I actually meant was 1 over t y. There we go. So here's a case for doing the integrating factor method. We're going to find rho that's equal to e to the e to the integral of p of t, which is just this term right here, 1 over t dt. That's going to give us e to the ln t, or just t. So now we know that we can solve this by setting up y of t is equal to 1 over rho of t, which is just 1 over t, multiplied by the integral of q of t, this guy, multiplied by rho, 3t squared minus 2t plus 2 dt. This will give us y of t is equal to 1 over t times t cubed minus t squared plus 2t plus c, and we can solve for c using this initial condition. Y at 1 equals 2, so 2 is equal to 1 times 1 minus 1 plus 2, I'll simplify things down here, 2 plus c. So we see that c is equal to 0. So knowing that, we can solve for y of 2 pretty easily. Y of 2 is equal to 1 over 2 times 2 cubed, 8, minus 2 squared, 4, plus 2 times 2. That's going to give us 8 over 4, or just 4, so 1 is C. 2, let's find the solution to this initial value problem. Immediately we are seeing that we have a function of x over a function of y, so our equation is separable here. So let's multiply both sides by 2y minus 4 and multiply both sides by dx. We'll be left with 2y minus 4 dy is equal to 3x squared plus 4x minus 4 dx. We can integrate both sides. We will get y squared minus 4y is equal to x cubed plus 2x squared minus 4x plus c. We can go through and get rid of at least one answer choice. That looks like the only one that we can rule out now, and we're going to have to evaluate our initial condition to learn anything else. So y is equal to 3, x is equal to 1. So if y is equal to 3, this will be 9 minus 12 is equal to 1 plus 2 minus 4 plus c. This over here will give us negative 1. Over here we will get negative 3 plus 1 is negative 2. So we can replace c with negative 2 up there. And so we see that E is exactly this expression that we found here. So 2 is E. 3, initially a tank holds 40 gallons of water. So V of 0 is 40. I'm just going to write down the information as we go, with 10 pounds of salt in solution. So that's Q of 0 is 10. A salt solution containing 1/2 pound of salt per gallon, so that's CI equals 0.5, runs into the tank at a rate of 4 gallons per minute. That's RI equals 4. And the well-mixed solution runs out of the tank at 2 gallons per minute. RO equals 2. And from this information, we can plug everything into the equation that we know solves this system. dq dt plus R0 over V of t multiplied by q is equal to RICI. We can fill in all these blanks, but first we're going to have to make our v of t equation. We know that v of 0 is 40, and we see that every second 4 gallons come in, 2 gallons go out. So v of t is 40 plus 2t, because for every unit increase in t, we're going to gain 4 gallons and lose 2, so that's a net gain of 2 gallons. We're left with dq dt plus R0, which is 2 over 40 plus 2t, multiplied by q is RICI, which is 4 times 0.5, or just 2. I'm going to divide, simplify everything here down a little bit, and we're going to use integrating factor to solve this. We see that rho is equal to e to the integral of 1 over 20 plus t dt, where this is our p term that we have to raise e to the integral of. So that means rho is equal to, this is equal to e to the ln 20 plus t, or just 20 plus t. And so we can say that q of t is equal to 1 over rho, 1 over 20 plus t, multiplied by the integral of q, which is right here, 2 times rho 20 plus t dt. Let's see, I'm going to need a little bit more space to solve this. I'll stick this over to the side. Took a row with it, whoops. So this is going to give us 1 over 20 plus t multiplied by 40t plus t squared plus c, and all of this is equal to q of t. Now we have an initial condition. We know that when t is equal to 0, q is equal to 10. So 10 is equal to 1 over 20 times c. So c must be 200 for this to be true. Plus 200. I'll go make that change. And then finally, we're looking for y of 20. This is going to be a little bit of a slog. I'm going to get rid of all this actually. So y, not q, yes, y of 20. Other problems tend to call it q of t, but in this case I call it, they're calling it y of t. It doesn't make any difference to us. So q of 20 is equal to 1 over 40 times 20, which will be 800, plus 20 squared, so 400 plus 200. That's 600. 600 plus 800, or 1400. 1400 over 40, which is 140 over 4, which is equal to 70 over 2, which is equal to 35. So C is our correct answer for 3. Question 4. If y equals y as a function of x is the solution of this equation given right here, x greater than or equal to 0, and y at 1 is equal to 2, then what is y at e? Well, we know that if we can express everything over here as a ratio between x and y, y over x mainly, we can use the substitution v equals y over x, and v prime x plus v is equal to y prime. And if we substitute everything else, all this in, we will be left with a separable equation. And just to make sure that we remember it, this is a homogeneous first order differential equation. Okay, so let's get going with this. Y prime will become dv dx, x plus v. And we're setting that equal to, well, if v is y over x, that's going to become v. This will become 1 over v equals v plus 1 over v. Subtract a v from both sides and multiply, multiply our, or divide our dv out. 1 times 1 over dv, and flip both sides, and we're left with v dv is equal to 1 over x dx. Integrate, v squared over 2 equals ln x plus c. 2 ln x, the square root of 2 ln x is equal to y over x. We can multiply that x out, and y is equal to x root 2 ln x, and I'm not sure why I lost my c in the last step, but our c is still, plus c, is still very much there. So we're given an initial condition, y at 1 equals 2. 2 is equal to 1 times the square root of 0 plus c. So c must be equal to 4 in order for this to be true. And finally, we're looking for y at e. So this will be y at e is equal to e times the square root of 2 ln e plus 4. And all ln e is 1. So we're left with e root 6. E root 6. Option C is our correct answer for 4. Question 5, if the following differential equation is exact, select the implicit solution to the initial value problem given below. This thing is looking pretty exact, but again, as always, we do have to check it. If this is a function m, and this is a function n, then we are checking if my is equal to nx. My, in this case, is the partial derivative of m with respect to y. That will give us e to the x cosine y minus 2 sine x, and we're checking its equality with nx, the partial derivative of n with respect to x, which is e to the x cosine y minus 2 sine x, and then this term will disappear completely. So we are looking at an exact equation. These two sides are equal to each other. So all we're going to have to do is compare the results when we integrate m dx and n dy. So m dx, integral m dx, is going to give us e to the x sine y plus 2y cosine x. And on the other side, I always like to draw a line down the middle so I don't mix and match things. We are going to get e to the x sine y plus 2y cosine x, 2y cosine x plus y squared. We see that we have overlap with these terms here, so we're only counting them once. And then, of course, we are counting our y squared, and that's all equal to c. So overall, we have e to the x sine y plus 2y cosine x plus y squared is equal to c. And looking at our answer choices, we only have one that matches the correct signs and values that we have for this left side. But if we really want to prove it to ourselves and find the c value, we can plug in our initial condition of y0 equals pi. That will give us e to the x, e to the 0 sine pi, which is 0, plus 2y, 2 pi cosine 0, which is 1, plus y squared, which is pi squared. So that's where they're getting their 2 pi plus pi squared from. And all this, of course, is equal to c. So c, in the end, is our correct answer for question 5. 6. Which of the following statements is true about the equilibrium solutions of the autonomous equation given here? So first off, we need to find these equilibrium solutions, what they are to begin with. That's just the solution when this guy is set equal to 0. We'll have y equals 0, 3, and -3. Okay, so how are we going to work with this? Well, let's draw out a number line. -3, we have a line extending past that all the way to -infinity, 0, 3, and up to infinity. And all we need to do is check a value for all 4 of these intermediate intervals, because if we try to evaluate at any of these, we are just going to get 0. So let's do this. If we evaluate -4, y equals -4, we will get -4, 9 minus 16. So we'll have 2 negative numbers. This will give us a positive number, and we'll represent that by an arrow heading in the positive direction. What about -1? That will give us -1 times 9 minus 1. That's a negative number, and so we will draw a negative arrow. What about 1? That'll be 1 times 9 minus 1. 9 minus 1, a positive number. And finally, if we try y equals 4, we will get 4 times 9 minus 16, which is a negative number. There we go. So because if you start on either side of 0, solutions always flow away from 0. 0 is asymptotically, or I guess they're never using asymptotically with unstable, but it is unstable. So 0 is not semi-stable. 0 is unstable, and that actually only leaves us with A. And we see that both -3 and 3, like they are saying in option A, are asymptotically stable. If you start any solution curves below -3 or above -3, they will all tend towards -3, and the same thing. And the same thing for +3. So question 6, our answer is A. Question 7, let's use Euler's method to find approximate value of y at 0.2 for the initial value problem with step size h equals 0.1. So our general formula for this, y at n plus 1 is approximately equal to y at n plus h times y prime evaluated at n. So we can think of this visually as if we have a curve like this, taking the value of y at this point and drawing a straight line with the slope of the tangent line at that point and approximating like so. And you can see it's not completely accurate, especially my drawing skills, but hopefully you have a little intuition of what is actually going on behind the scenes here. So we are given that y of 0 is equal to 1, and we are approximating. Our first approximation is y at 0.1 is approximately equal to y at 0, which is 1, plus h, which is 0.1, times y prime evaluated at 0, 1. That's going to give us 1 squared plus 0 squared, so 1, and so this is equal to 1.1. Now we have our new condition to work with. We have that y at 0.1 is equal to, or is approximately equal to 1.1, and we can take that and use it for our final approximation step. We will see that y at 0.2 is approximately equal to y at 0.1, so 1.1 plus 0.1, our step size, multiplied by this guy right up here, our y prime evaluated at this condition. and that will give us 1.1 squared plus 0.1 squared. And there are a lot of ones floating around here. 1.1 squared will give us 1.21, and 0.1 squared will give us 0.01. So together these give us 0.22 times 0.1 is 0.122 plus 1.1 is approximately 1.222. So E is our correct answer for option 7. Question 8, the largest interval in which the solution to this initial value problem is guaranteed to exist by the existence and uniqueness theorem is what? Immediately, whenever we see something like this, it doesn't matter whether it's first order or second order, we have to make sure that our highest order derivative is by itself. So rearranging y double prime plus t minus 4 over 5 minus t y prime plus 2 over 5 minus t y is equal to ln t over 5 minus t. We know that all we're looking for here, given that our initial condition is at t equals 7, we are looking for the largest or the longest distance that we can head to the left and to the right without hitting any of the discontinuities for any of these functions. Let's see, these functions are discontinuous when t is equal to 5, because that will make the denominator in all three of these 0, and when t is less than 0, because we have an ln t which is not defined for negative numbers. And since we're sitting at 7, we are going to hit 5 in this direction, and we are going to hit infinity in this direction, because we have no upper bound to worry about here. So 5 to infinity, 8 is E. Question 9, given that the function y1 is equal to t as a solution to this differential equation, we're trying to find y2 such that the pair y1 and y2 is a fundamental set of solutions for the differential equation. Our equation for this is y2 of t is equal to y1 of t multiplied by a really big integral, an integral of e to the negative integral p of t dt all over y1 of t squared. So it looks like a lot, and it kind of is a lot, but it's going to simplify down relatively quickly. We're going to have to, in order to find this p of t, like usual in all these problems, we're going to have to divide out t squared in order to keep y double prime by itself. So y double prime minus 1 over t y prime plus 1 over t squared y is equal to 0. So our p value is given right here. We're going to need e to the negative integral of 1 over t dt. We can cross out both these negatives. This will be ln t, and e to the ln t is just t. So all of this up here is simplifying down to t. Now moving down to our denominator, we are told that y1 is equal to t, so y1 of t squared is t squared. We can also replace this y1 of t out here with a t. So our integral can be rewritten as y2 of t is equal to t times the integral of 1 over t dt, which is equal to t ln t plus tc. And since this c can be equal to 0, our fundamental, or one of our possible solutions, the fundamental solution is just t ln t, getting rid of this section here. So B is our answer. B is our answer for number 9. And that's it. That's it. That's all we can do from here. Yeah, nice. This was almost one take. I have to cut a cough. I'm cutting a cough out from question one, but other than that, yeah, I never know what to say here anyway. See ya.